Good afternoon. My name is Edgar Gabriel. In the next couple of minutes, I would like to present our work on parallel I/O on compressed data files, a paper that we originally submitted and got published in CCGrid 2020. This work was done jointly with Siddhesh Pratap Singh, a PhD student in my group at the University of Houston. And to give credit where credit is due, much of the hard work, the implementation, etc., was done by Siddhesh. So, a brief outline of this presentation. I will first give a very brief motivation and introduction to the problem that we try to solve with this publication. I will then give a brief overview of the most relevant conceptual aspects of our work, as well as provide some details of our implementation of this work in the OpenMPI Parallel I/O library. The most significant part of the presentation will be devoted to the evaluation aspect, where we evaluate the benefits of using compressed data files in parallel I/O. And finally, I will conclude the presentation by summarizing our contribution and present some ideas for future work. So, large-scale parallel applications have often worked or are more commonly working on very large data files. So simulations that utilize data files that are in the hundreds of gigabytes size range are not unusual at this point in time. There are multiple methods on how parallel applications can access and utilize these very large data files. MPI-IO is one of the popular API used by very large parallel applications due to the numerous optimizations that it introduced for managing large data files from parallel MPI applications mostly. The two most important optimizations or concepts that have been introduced by MPI-IO are the notion of a file view, where a process can declare ahead of time which parts of a data file it intends to access, and the notion of collective I/O, which is basically a group I/O file I/O operation that allows to reorder data across processes internally, such that the data access now matches the data layout on the file system level, and because of that can minimize file locking contention. So MPI-IO, as it is defined right now, operates on flat data files. And what that specifically means is the data cannot be compressed in order to utilize MPI-IO. This is, however, a problem for multiple reasons. One of them is that very commonly large data files are being compressed to reduce the file size that it takes up on the storage system, or when you download the large data set from the internet. If you would like to utilize a compressed data file with an MPI application that uses MPI-IO, basically what you would have to do right now is initially decompress the data file, run your MPI application, and then the resulting files, you have to compress them again sequentially afterwards. So basically, operating with compressed data files in MPI-IO at this point involves some potentially very expensive pre- and post-processing steps. And this is really addressed in this work. So we try to analyze and address how can we extend the concept of MPI-IO to operate on compressed data files. And as part of this work, we also extended the two-phase I/O algorithm that is the most popular algorithm used for collective I/O operations to operate on compressed data files. Now, the goals of what we try to achieve with this work basically were manifold. So one of the aspects that we were really trying to focus on is that an existing MPI-IO application should ideally be able to operate without any changes, or at least without any significant changes, on compressed data files. So you should be able to use the same sequence of file open, file set view, file read, file write as for a regular non-compressed data files up to now. Second, MPI-IO has ultimately been designed with the idea of maximizing performance overall, and this of course holds also true for compressed data files. So a solution that would basically internally write first an uncompressed data file and then compress the data file on file close, for example, that would not be performed by any reasonable means or for any reasonable size data file. So we try to avoid that. The compression has to be part of the fundamental operations of the MPI-IO library. And last but not least, we would like to avoid violating any rules laid out by the compression library. So most notably, if a data file has been written outside of an MPI application, so for example in a Hadoop or with a sequential tool such as gzip or bzip compressed data file, you want to be able to use that within the MPI-IO interfaces or within the MPI application. And of course, the opposite is also true, that a data file that has been written with our MPI-IO implementation capable of creating compressed data files, that data file has to be a valid gzip, bzip, snappy, whatever compression algorithm you are using, and you should be able to use the resulting file also with other applications or tools outside of MPI. Now, our work also identified, however, a number of restrictions and limitations that we have to take into account. So first, most compression algorithms do not tolerate gaps in the compression format. So, and this is really important in the parallel I/O scenario, and I will give you a couple of examples later on. Second, our approach mandates that for write operations, we have monotonically increasing offsets. So think of it that way: if you would be allowed to go back and overwrite an existing part of a file, compression really depends on the actual data that is being written. And how well data compresses depends on how much repetitions is in a particular data block. You have no guarantee that just because you have an uncompressed buffer of, let's say, 2 kilobytes, the compressed size will be the same twice for different values, right? So in theory, if you would be allowed to go back and overwrite an existing data block, you might end up with a smaller or a larger compressed buffer as a result of the compression, and ultimately you would either end up having a gap in your compressed data file, or you would potentially overwrite some existing data. For very similar reasons, individual write operations are only permitted from a single process. And interestingly, MPI-IO actually has already a mechanism that allows to specify for that. Again, the reasoning is very similar to what I described with the monotonically increasing offsets, but I would like to point out right now that that if you would like to write data from multiple processes, there are solutions that you can use, such as collective I/O and shared file pointer operations, instead of individual write operations. For read operations, there are no fundamental restrictions. And I would like to point out that there's also a restriction or a requirement for compression algorithms that can be used in this scenario. Fundamentally, the algorithm itself has to be able to operate on a chunk by chunk basis. So algorithms that would compress the data based on the entire file are not feasible candidates. So conceptually, again, let's talk briefly about individual I/O. So for individual write operations, the approach is relatively simple because you basically allocate a temporary buffer, compress the user buffer, and write the compressed data to file. For read operations, it is very similar. You allocate a temporary buffer to store the compressed data. You read the chunks from the compressed data file that contain the requested data items, uncompress the data, and copy the requested elements from the temporary buffer into the user provided buffer, right? It is important here to understand that there's no guarantee that a compressed data chunk is fully requested within an individual I/O operation. And in fact, you might have to read more compressed data in order to be able to decompress the chunks that contain your data items correctly. For read operations, I will not go into details here, but it is, from the performance perspective, it's really important to be able to quickly identify the part of the file that contains the data items requested by the application. And fundamentally, one has to be aware of that the MPI-IO operations posted by the application still operate on uncompressed offsets. So we have to be able to quickly do a mapping of an uncompressed offset to the compressed offset in the file where the data would be located. And for this, we introduced the notion of an annotation file, which is basically like an index for every compressed chunk of data, and it allows us to narrow down very quickly where the data is located that is being. The most significant algorithmic contribution of this work is coming from collective I/O, where basically multiple processes write or read data simultaneously. We are focusing in this work on the write operation, and the most relevant algorithm used by collective I/O implementations at this point in time is a two-phase I/O algorithm, which, as discussed earlier, rearranges data across processes in order to match the file on layout on the file system level. This is often referred to as the shuffle step. And then a subset of the processes, the so-called aggregators, perform the actual write operation. Our work now included extending the two-phase I/O algorithm to make compression seamless. And there are numerous trade-offs that I cannot go into details here. Is, for example, where to perform the compression on the processes, on every process individually, or on the aggregator side, and so on. We went for the solution where each process performs the compression by itself, and the aggregators perform, however, the calculation of, or the recalculation of, offset and length for the compressed data. So, brief overview, and again, the details are given in the paper. So first step of the two-phase I/O algorithm, the compression and the shuffle phase. So what will typically happen is that every process initially communicates an array or a list of their offset and length tuples of the data items that they would like to write. We now basically have to extend that list to also for every data block to include the compressed size as well. And this metadata communication, this offset length arrays or lists, this allows every process to determine when they need to send what data item to which of the aggregators. Again, with the compression information now, in addition, the metadata information increases, followed by the actual data communication, where the actual data items are being sent to the individual aggregators. The aggregators take the data from the individual processes and write it to file, concatenate it in the correct order based on the offsets, and then write the data. Now, with our extended two-phase I/O algorithm, they also need to perform a recalculation of the actual offsets used for each compressed buffer. So we basically need to distinguish between the uncompressed offset that was provided as part of the MPI-IO API and the compressed offset that is the result of the compressed length of the data and the sum of the compressed length of previous data chunks, right? The algorithm then still allows to perform the write operations in parallel without leaving gaps, and yeah. So again, the details of the algorithm are given in. So a couple of words to the implementation. So the implementation was performed using OpenMPI based off the master branch that was retrieved, I think, approximately 2019. It is using the OMPIO components and the architecture overall, and we developed 3 different components. The Composites component that implements individual I/O operations for compressed data files. WULCOMP, an extension of the Vulkan collective I/O component used by OpenMPI, again to support compression, and the clocked file component that allows to manage shared file pointer operations for compressed data files. As a compression library that we are using right now the Snappy compression library developed by Google, because this algorithm or this library was designed with parallel processing already in mind, and it's actually a very popular compression library in the data science community. This is a proof of concept implementation, so it's not part of any release branch, and we don't make the claim that it's completely bug-free, but we are confident that the results that we present are correct, right? And it is available for download at the address shown. Performance evaluation was performed on the Krill cluster at our university using a BGFS file system that has 16 storage servers, 1 megabyte stripe size. Two different set of tests are being performed. One is the matrix tests that basically utilize artificially generated matrices. Since compression relies on repeatability and repetitions in the data set, what we did was we generated a fixed set of floating point values, and the matrix is populated by randomly picking values from this fixed set, from this bucket of available values. The size of the bucket also allows us to control the compressibility of the data, and we performed 1D and 2D data decompositions with the data items. We also performed then some real-life data and some compression tests and some performance tests with real-life data sets that vary between 16 and 77 gigabytes. So for the matrix tests, the results are shown here. So we ran a number of different process counts. Up to 529 is presented here. The two values that you see at the bottom, the 2048 and 4096, are the size of the matrix on a per process basis. So basically the overall amount of data increases linearly with the number of processes used. But fundamentally the results are very encouraging because, again, due to the reduction in the data size that has to be written, we are able to reduce the time it takes to perform the collective write operation in all of these test cases quite significantly. We took them one test case and performed a detailed breakdown of where time is being spent. So the difference in this test compared to the previous ones is that the overall amount of data stays roughly the same across the different process counts. And so the most expensive operation is the write operation itself performed on the aggregators. And since the overall amount of data is fixed across the different process counts, and because the write time itself is at this point in time limited by the bandwidth of the storage system in this environment, that value stays roughly the same. The compression time, that's the green part of the data, decreases with increasing process count, which makes sense because you're using more and more processes to compress a fixed amount of data. The metadata communication increases, however, because you have more and smaller chunks of compressed data that you need to manage overall. So ultimately, the results make sense on many levels. Next, in this set of tests, we played around with the bucket size and achieved various compression ratios. And as expected, I mean, the higher the compression ratio, the smaller the actual amount of data is that needs to be written with a collective I/O operation. And as expected, the smaller the data size, due to a better compressibility, the better the overall performance. Last but not least, some tests with real-life data sets where we compare the time it takes to sequentially read and compress the data versus using the parallel version. I will not provide detailed analysis for these scenarios due to the time limitations, but basically, as you can see on this slide, is we can achieve quite significant speedups by using an MPI-IO based version of a snappy compression, right? So whether you have 64 processes compressing a 77 gigabyte data file, that will be quite a bit faster than if you perform it sequentially. So to summarize, we defined semantics and rules for parallel IO compressed data files. We identified also limitations on what can and cannot be done. The applications that we've used here are really using MPI-IO as before in the code. The only change really was that we're using an info object to indicate whether we want to have compression or not, right? But other than that, compression and decompression is basically handled seamlessly by the implementation. So future work, we plan to extend our work to more compression libraries, although we hit there some interesting results and challenges with some of the other compression libraries out there. And we are working also at the same time on defining an internal MPI specific file format to support multiple compression formats simultaneously, because compressing floating point values, you might need very different compression algorithms than compressing integer or characters, right? So our goal in that second aspect of the work is to really have like our own compression format that might utilize internally multiple compression algorithms. So that's basically it. Thank you very much. And if you have any questions, please don't hesitate to send us an email or ping us any other way. Thank you.